So folks, in this sequence of videos, we're going to do a lot with the definite integral, but before we do that, I thought I'd do a little bit of a review just to make sure we're comfortable with some of the older topics. So here we're given the function g of x is equal to the cube root of x plus 1 divided by the cube root of x. The first question says to find g prime of x. So as we've seen many times, it is easier to compute derivatives when you first rewrite these expressions as power functions. So I'm going to rewrite this as x to the 1/3. And then I could rewrite this as, for the second term, I'll first rewrite it as plus 1 over x to the 1/3, but then I can rewrite that as the first term, and then I'll rewrite the second term as x to the minus 1/3. Notice at this point, and I've told my reader that I'm just dealing with g of x. Now I'm ready to compute g prime of x using my power rule. So that's going to be 1/3 x, and then we subtract 1 from 1/3 to give me minus 2/3 for the first term. And for the second term, we will get minus 1/3 x to the, and then if I subtract 1 from minus 1/3, I get minus 4/3. Now that's an answer, but usually we do a little bit of rewriting. Any exponents that are negative we put below the line, and so we'll end up with 1 over 3x to the 2/3 minus 1 over 3x to the 4/3. Now I could do some other rewriting, I could write these different ways, but that's a good enough place to park our answer. Okay, this second question says to find an antiderivative. So this is what's a little bit challenging now, folks, that we've learned both computing derivatives and antiderivatives. Now I have to perform the power rule backwards to compute the antiderivative. So we're going to say that our g sub x, the capital G, remember that stands for the antiderivative, that's going to be the antiderivative of, and then I'm going to say of g of x dx. Now careful, folks, make sure you have both the integral symbol and the dx until you've evaluated the integral. So make sure you have both of those. And then that's going to be the same thing as computing the antiderivative. Now, because in the line above I already did some rewriting, I can go ahead and rewrite this as x to the 1/3 plus x to the minus 1/3 dx. But again, if I hadn't already rewritten this, I would have taken the original function and put it into a form where I can readily apply the power rule. So now I feel confident that I can go ahead and apply the power rule for antidifferentiation. So just as a reminder, when we go to compute the antiderivative of x to the n dx, that's equal to x to the n plus 1 divided by n plus 1 plus c, and that holds for n not equal to -1, which is its own special case. So I'm going to go ahead and apply this rule to each of these expressions. So adding 1 to my power function gives me x to the, well, that's 1/3 plus 1, which is 4/3, and then dividing by that new exponent gives me 3/4. Performing the power rule on the second term, we're going to add 1 to the power. So if I add 1 to minus 1/3, I get x to the 2/3, and then I'm going to divide by that new exponent, so I get 3/2 plus c. Folks, the easiest thing in the world, I think, at this point is to check your work. Doing the antiderivative is typically more difficult than doing the derivative, and so it's easy to go ahead and compute the derivative of this term, and notice you get the term above it, and compute the derivative of this term, and notice you get the term above it. So we're on track. Now, in this case, this is the antiderivative, but I've given you some additional information to enable you to figure out what g of x is. And that is, we're going to use this information here, we're going to use this to find c. So if we go ahead and do that, I'm going to plug a 1 into this function here, and I'm going to then set it equal to 17/4. So I get 3/4 times 1 to the 4/3 power plus 3/2 times 1 to the 2/3 power plus c, and I'm going to set that equal to 17/4. Cleaning things up, I've got 3/4 plus 3/2. That's a total of 9/4 plus c has to equal 17/4. And so we find that c, in this case, would be 8/4 or 2. Okay, so I'm going to clean this up, folks. Sorry to make that a little bit too big here. Let me clean that up some. scrunch this down. There we go. And now I feel ready to give my final answer as to what g of x is. Let's scoot over here. And we will say that our g sub x, is going to be 3/4 x to the 4/3. And while there are many ways I could rewrite this expression, I'm kind of happy writing this as x to the 4/3 power, plus then 3/2 times x to the 2/3, plus my c value, which I just computed over here. Using this initial condition, I was able to figure out that c has to be 2, so I just add that c value there. And let me just scrunch that down a little bit. Okay. And there I found the antiderivative, g of x. So if you were to take the derivative of this function, if you take this function's derivative, sure enough, you would end up with the original little g of x. But also, if you were to plug 1 into this function, you can confirm that it equals 17/4. Okay, so let's try the next problem here. So in part B here, we're just asked to compute h prime of x. And again, this is just some practice with some rules we've used many, many times before. The derivative of the sine of x is the cosine of x. And the derivative of 1 over x is minus 1 over x squared, and there's the answer. If you had trouble with that last part, remember when we go to take the derivative of 1 over x, we first have to think about it as being x to the minus 1 power, and then we apply the power rule to it, the power rule for differentiation, and then I could rewrite that as minus 1 over x squared, which is what I did. Scoot over just a little bit. For h of x here, finding the antiderivative, notice that this is not, compare and contrast this with this earlier question. I'm asking for the antiderivative, but I'm not going to tell you enough information to find the specific function, so we will have a general c in our answer. So just practicing that here. The antiderivative of h of x, and we're practicing using this notation here, that's equal to the antiderivative of the sine of x plus 1 over x dx, which is equal to minus the cosine of x plus the natural log of the absolute value of x plus c. And you can check this simply by taking the derivative minus cosine. You can confirm that you get sine. And simply by taking the derivative of, well, the natural log of x was 1 over x, but that's also the derivative of the natural log of the absolute value of x. Folks, that works through B. We'll jump into C next. Scrolling down. Oop, a little far. So here we're just getting some more practice. I'm going to practice my product rule on this. So let's see here. We're given k of x is equal to this function here. Find k prime of x. So I'm just going to compute k prime of x. Here I'm going to have to do the product rule between the secant and the tangent of x. So that's going to be the first function times the derivative of the second. So there's my secant times the derivative of the second, which is secant squared of x, plus then I take the derivative of the first function, which is secant x times tangent x times the second function. So there's a lot of secants and tans in this problem. Let's make sure we're comfortable with what's what. So I'll call this the first, and I'll call this term the second. And so you can see what I did here is I gave the first function, I multiplied that by the derivative of the second function. Then I took the derivative of the first function and I multiplied it to the second function. That's how we perform the power rule. And then we could go ahead and take the derivative of the second function. Now be careful here, and it might be worth rewriting this. This is the function secant x tangent x, and then I've warned you a few times over the course of this semester that it's helpful to rewrite this function as the secant of x squared to help you see that chain rule that we're going to have to do on this second term here. So we're going to add to that plus 2 times the secant of x now to the first power times, and then if I take the derivative of what's inside there, the derivative of the secant of x is another factor of secant x tangent x. Folks, I could take some time to clean this up. I will add on to your directions here. Do not simplify. I don't want to worry about cleaning that up now, although you should feel comfortable cleaning that up if you had to. Okay, the next question asks me to go ahead and find the antiderivative capital K of x for this function. So here we go, capital K of x, is equal to the antiderivative of k of x dx, and then I'll just insert what k of x is. K of x is this large expression here, secant x tangent x plus secant squared x dx, and now I'm going to anti-differentiate each of these terms. Well, we're lucky here because ordinarily I might have a really hard time finding the antiderivative of this expression because I can't use a power rule on it, and I don't have a lot of tools for differentiation at this point in our math career. You'll get more tools for finding antiderivatives when you get to Calculus 2. But when I'm looking at this expression secant x tan x, I recognize that as the derivative of the secant function. So for this first term here, when I go to anti-differentiate that first term, it's just going to be the secant of x right there. And then I recognize that right here I have the secant squared of x, and I know that the secant squared of x is the derivative of the tangent of x. So again, ordinarily, if this were just some massive trig expression, I might be in trouble. But this is what I like to call an elementary antiderivative. And so I recognize that when I took the derivative of the tangent function, I got secant squared, so I'm just going to add to that the tangent of x, and don't forget your plus c. So just to clarify, the antiderivative of this second term right here was the tangent of x plus c. Folks, some of you are still having some errors here, so I just want to highlight something. Notice that when I went to go compute capital K prime of x, I wrote my antiderivative symbol with the dx. I do need that dx. If you're missing that, you're going to be marked wrong, or at least lose a point. Notice here, I did not evaluate the antiderivative. All I chose to do was replace k of x with this long expression for k of x. So I continued to write my antiderivative symbol dx. But notice that when I went from this expression right here to this expression here, I took the antiderivative, so I stopped writing my integral symbol and I stopped writing the dx. Folks, if you have any questions on this, please let me know. So now, folks, we're asked to compute L of x, which is again to compute an antiderivative of k of x, but in this case we're told L of 0 has to be 4. So rather than having a plus c in our answer, like we did in this standalone problem here, we're going to actually be able to solve for the specific constant that not only makes k the derivative of L, but also has the fact that L of 0 equals 4. So let's see if we can figure that out. So we've already done the work, so we know L of x from this work above here is going to be the secant of x plus the tangent of x plus c, but we're going to add to that when we plug in 0 in for x, L of 0 needs to equal 4. So I'm going to say that 4 needs to equal the secant of 0 plus the tangent of 0 plus c. Now, the tangent of 0 is 0, and you can see that by looking at the graph of your tangent curve. And the secant of 0 is 1, and again, you can see that by looking at your secant curve, or there are many other ways you could argue that. So anyway, we end up with 4 is equal to 1 plus 0 plus c, so I find that c is equal to 3. Careful, folks. Resist the temptation to say that your answer is c equals 3. Remember, solving for the constant c was just one step in finding this function, capital L of x. So now I'm ready to give my answer as capital L of x is equal to the secant of x plus the tangent of x plus 3. And there we have the solution to part 3 there. Okay, scrolling down, scooting over a little bit. Now we're asked to compute this integral. Notice in this case, this is not an indefinite integral. In this case, unlike the previous two problems, I do have limits of integration. So ordinarily, I might have to start and do a whole bunch of work, but in this case, we've already computed the antiderivative of this function, so we'll just go ahead and take that. So we're computing this definite integral here. Remember, this is finding the area underneath the curve. We're going to find this definite integral here. Let's go ahead and do so. So we already know that an antiderivative of this function would just be secant of x plus the tangent of x. And we could pick a c value, like we could pick c equals maybe 3 like we saw before, or c equals 25, or any number we wish for c. But the easiest number to pick is c equals 0, and we don't write that expression here. Now we're going to say let's evaluate it between the upper and lower limits of integration. Folks, notice between here and here, what did I do? I said I'm going to compute this definite integral. To do so, I will give an antiderivative of this function. Any antiderivative will do, and I'm going to evaluate it at its upper and lower limits of integration. So folks, you definitely need to have that evaluation bar right there. So now we're ready to use to evaluate this, and this is what this evaluation bar is sort of shortcut for. It's shortcut for writing the secant of your upper limit of integration, or saying that again, we're going to evaluate the antiderivative or an antiderivative at the upper limit of integration, and then we're going to subtract from that the antiderivative evaluated at the lower limit of integration, secant of 0 plus the tangent of 0. Okay. So just going through and evaluating these, this is going to be evaluated to be 0. We've already discussed this will evaluate to be 1. Remember that the tangent of pi over 4 is 1, and the secant of pi over 4, to be honest, I don't remember that, so I'm going to have to check. If I go draw a unit circle here, here is my unit circle, and I want to go to the angle pi over 4, which would be this angle right here. We've got the ordered pair pi over 4, excuse me, we've got the, that's for the angle pi over 4, let me label that. That's for the angle pi over 4, and we've got the ordered pair radical 2 over 2, comma radical 2 over 2. And remember that this will be my x coordinate goes with, or excuse me, my y coordinate goes with sine, and my x coordinate goes with cosine. But remember that the secant is 1 over the cosine value. So this is equal to 1 over the cosine of pi over 4. Everything else is kind of straightforward to evaluate. We got plus 1 and minus 1. And then if you wanted to be really careful, you'd have a minus 0, distributing this minus sign to both terms. Okay. Here, these two terms will add out, and I'm just left with 1 over the cosine of pi over 4. But we just said to find the cosine on the unit circle, we take the x-coordinate of that point. So we're going to end up with 1 divided by the square root of 2 over 2, which I could rewrite as 2 divided by the square root of 2. I'm happy with that answer there. Most textbooks would go ahead and rationalize your denominator and say that the answer is just the square root of 2, and you can check if you multiply this by square root of 2 over square root of 2 that you get this answer as well. But I'm perfectly happy with this answer. Folks, I hope this was a helpful review of many of the procedures that we've done in this course. Please, folks, at this point in the semester, if there's anything in this problem that's giving you any trouble at all, please let me know.